In this episode, we will talk about scaling law for quantization-aware training. Okay, let's dive in. Large language models, LLMs, they're amazing, no doubt. But let's face it, their size is it's a massive hurdle,
It really is. We're talking billions, sometimes even trillions of parameters.
which needs huge compute, huge memory,
hmm
makes running them efficiently, outside of these giant data centers really tough.
That's the core challenge, exactly. Getting these powerful models onto devices or even just regular servers is really bottlenecked by how big they are.
And that's where quantization comes in, right?
Precisely. It's a really fundamental technique to try and shrink these models down, make them faster. Basically, you reduce the precision of the numbers inside the model.
Right, like instead of using a full 32 bits for every number, maybe you drop to 8 bits or even 4 bits.
Or less sometimes, yeah. And that saves a lot of memory and speeds up calculations.
But just doing that after training, that's post-training quantization, PTQ, that often hurts performance, doesn't it? Especially when you go really low, like 4-bit for everything.
Yeah, especially at those really aggressive levels like W4A4, that's 4-bit weights and 4-bit activations. PTQ really struggles there.
The model just wasn't trained for that kind of low precision.
Exactly. It hasn't learned to cope with that reduced information, and that's why quantization-aware training, or QAT, is generally the way to go for these low-bit scenarios.
Because you build the quantization into the training process itself.
Right. So the model learns, it adapts to work well. Even with those tiny 4-bit numbers, it compensates during training.
Okay, so QAT helps a lot. But there's still been this kind of open question. How does that QAT performance actually scale? Like, how does it change with model size or training data or even the details of the quantization?
Yeah, the existing scaling laws, even the early ones for QAT, they didn't always capture the whole picture. They often miss some really crucial factors.
What kind of factors?
Well, things like the amount of training data, let's call that D, and also the quantization granularity, G, which is basically how you group numbers together for quantization. These turn out to be really important for QAT, especially at W4A4.
And that's what this new research tackles.
Exactly. This paper we're looking at from the University of Hong Kong and ByteDance Seed, it's dated May 21st, 2025, aims to build a unified scaling law for QAT.
Unified, meaning it pulls together model size N, training data D, and this granularity thing G all into one framework.
That's the idea. So in this deep dive, we'll unpack what they found, how that quantization error, the performance gap, relates to N, D, and G, and crucially, where the errors mainly come from in W4A4. Understanding that is key to improving it.
Okay, let's set the stage a bit more. We know about classic LLM scaling laws,
Yeah.
right? Like Chinchilla. They tell us how loss relates to model size N and data D.
Right, those were foundational. They showed, for instance, how you should balance growing your model versus getting more data for optimal, full precision training.
So when people started looking at QAT scaling, they kind of built on that.
They did initially. They often took those classical laws and tried to adjust the model size part N to sort of account for the lower precision, like an effective size.
But they missed the D and G effects you mentioned.
Largely, yeah. Or they didn't integrate them properly. And this paper's experiments really highlight why you need to include D and G for QAT. They ran a ton of W4A4 QAT experiments, systematically varying N, D, and G.
And what did that data show?
It clearly showed that the quantization error, which they measure as the difference in validation loss between the QAT model and a full precision model, trained the same way that error changes significantly with both D and G. It's not just about N.
Okay, so you can't just tweak the model size factor and call it a day.
Doesn't look like it, especially for W4A4. So their big idea was, let's not just try to predict the final QAT loss. Let's directly model that quantization error, which they call deep delta P.
So deep is the penalty you pay for doing W4A4 QAT compared to full precision.
Exactly. And they wanted to find a formula where deep depends directly on N, D, and G.
And their experiments gave them clues about what that formula should look like. What were the key observations for W4A4?
3 main things stood out from their data, looking specifically at W4A4. First, as model size N gets bigger, the quantization error tends to go down.
Okay, that makes sense. Bigger models might be more robust to the noise from quantization.
Seems plausible, yeah. More capacity to maybe work around the approximation errors. The second observation, though, looking at training data D was really interesting, maybe even a bit counterintuitive.
Wow.
They found that the quantization error actually increases as you use more training tokens, D.
Wait, hold on. Increases. More data usually makes models better. Are you saying the quantization penalty gets worse with more data?
That's what their results indicate, yes.
Okay.
Even if the final QAT model trained on more data performs better overall, the gap between its performance and a full precision model trained on that same large data set actually widens.
Huh. Why would that be?
Well, the thinking is that training on more diverse and complex data might expose the limitations of that fixed 4-bit representation more starkly. The full precision model can leverage the rich data better, while the W4A4 model hits its representation limits sooner, widening the gap.
Okay, that's a really key finding. What was the third observation?
The third one was about granularity, G. This was maybe more expected. The quantization error depth decreases as the granularity gets finer.
Meaning smaller group sizes for quantization.
Exactly. When you quantize numbers in smaller chunks, you can generally represent the values within each chunk more accurately. Coarser granularity, larger groups, leads to more error.
So based on those three trends, error down with N, up with D, down with finer G, they built their mathematical scaling law.
Right. They proposed a formula for EP with terms related to N, D, and G, each with its own exponent or coefficient, reflecting how sensitive the error is to that factor. They fitted this formula to their, I think it was over 80 W4A4 QAT runs.
And did it fit well? Did it actually predict the errors?
Yeah, they showed it fit the experimental data very well. The fitted parameters confirmed the trends. Positive sensitivity to D, error increases. Negative sensitivity to N, error decreases. And positive sensitivity to group size G. Error increases with coarser G, meaning decreases with finer G.
And could it predict beyond the data they trained it on? Like extrapolate?
That's the important test, right? And yes, they showed it did a good job extrapolating, predicting errors for models up to nearly 1 billion parameters trained on 100 or 200 billion tokens, which were significantly larger scales than most of the runs used to fit the law. That suggests it's quite robust.
Okay, so we have a way to predict the total W4A4 error based on N, D, and G, but W4A4 quantizes weights and activations. Where does that error actually come from? Is it mostly the weights, mostly the activations?
That's the crucial next question for actually improving things. You need to know where the bottleneck is. So they designed experiments to decompose the error.
How do they do that?
They trained specific models. One type they called W4A16, where only the weights were 4-bit, and the activations stayed at a much higher precision, effectively 16-bit or float.
Okay, so W4A16 isolates the error just from quantizing the weight.
Correct. And then they did the opposite, W16A4, where the weights were high precision, but the activations were quantized down to 4-bit.
Got it. W16A4 isolates the activation quantization error.
Exactly. And what they found was pretty neat. The total error they measured in the original W4A4 models was very, very closely matched by just adding up the error from the W4A16 model and the error from the W16A4 model.
Ah, so the errors are roughly additive. W4A16 plus W16A4.
Pretty much, yeah. They found the sum explains something like 90% of the W4A4 error. This is great because it means we can analyze the weight and activation errors separately using these specialized models and understand their individual contributions.
Okay, so how do these weight errors from W4A16 and activation errors from W16A4 scale differently with N, D, and G?
They both generally follow the same broad trends we saw for the total error, down with N, up with D, down with finer G. But the strength of those trends, the sensitivity, is quite different.
How so?
Okay, so the weight error, W4A16, seems to decrease faster as model size N increases, but it also increases faster with more training data D.
So bigger models handle weight quantization better, but bigger data sets make weight quantization relatively harder.
That's what the sensitivity suggests, yes. Now compare that to the activation error, W16A4. Its sensitivity to model size N and data D was less pronounced than the weight errors, but its sensitivity to granularity G was much higher.
Activation error is super sensitive to the group size.
Dramatically so. It drops off much more sharply as you make the quantization groups smaller, finer granularity.
And why would activation error be so much more affected by granularity?
The paper points strongly towards outliers in the activation values. Activations, especially after certain operations, can have these occasional very large or very small values.
Right, outliers.
And when you use coarse granularity, a large group size, you're trying to represent a wide range of values, including potential outliers with just one or two scaling factors. That really struggles with outliers. finer granularity lets you use different scaling factors for smaller ranges, handling those outliers much better.
Makes sense. So we know weight error grows faster with D. Activation error is very sensitive to G. Overall, in typical W4A or 4 scenarios, which one tends to be the bigger problem?
Generally, across most of the settings they tested, the activation error, W16A4, was larger than the weight error, 14A4A16.
So activation quantization is usually the main bottleneck for W4A4 performance.
It appears to be yes. That's where most of the error tends to come from initially.
Does that balance ever shift, though, depending on N, D, or G?
It does. They looked at the ratio of activation error to weight error. As the data to parameter ratio, DN, goes up, meaning you have relatively more data for your model size, that ratio tends to decrease.
Because of weight error grows faster with D, as you said.
Exactly. So weight error becomes a relatively larger part of the total error. Conversely, as the quantization group size, G, gets larger, making granularity coarser, the ratio increases.
Because activation error is so much more sensitive to that coarse granularity.
Precisely. So activation error's dominance grows in that case.
Okay, so baseline. Activation errors are probably your bigger worry for W4A4. But if you're using huge data sets relative to model size, weight error starts demanding more attention. So focusing on that application bottleneck first, how did they try to fix it?
Right. Since activation error seems linked to outliers, they tried to pinpoint where in the typical transformer architecture these outliers were causing the most trouble for 4-bit quantization.
Did they find a specific spot?
They did. They used a statistical measure called kurtosis, which basically indicates how peaky a distribution is and how heavy its tails are a sign of outliers.
Okay.
And while QAT generally helps reduce kurtosis, meaning fewer outliers, in most layers compared to non-QAT models, they found one particular layer input consistently had significantly high kurtosis even after QAT.
Which one?
It's the input to the second fully connected layer inside the feed-forward network block, often called the FC2 proj input or similar.
And why is that spot so prone to outliers?
It comes right after the SWGLU activation function or similar gated linear units. These nonlinear functions, while powerful, can sometimes amplify values, turning moderate values into more significant outliers that are then fed into that FC2 layer.
Ah, so that nonlinearity creates a distribution that's really hard to squash down to 4 bits accurately.
Seems to be the case. It's a known tricky spot.
So finding this specific bottleneck, what was their proposed solution? Just don't quantize that layer.
Not quite that drastic. They proposed a mixed precision approach. Keep most of the model at W4A4, but for this specific problematic input to the FC2 layer, quantize it to a slightly higher precision. They used 8-bit.
Okay. So a targeted intervention just for that one difficult tensor, W4A4 mostly, but W4A8 for the FC2 input activation.
Exactly.
And did that help? What was the impact?
It helps significantly. Using 8-bit for just that one input substantially reduced the overall quantization error. The improvement was especially noticeable when using coarser quantization granularities, larger G.
Which makes sense because coarser granularities struggle most with those activation outliers, and this fixes the worst source of them.
Precisely. It directly addresses the mechanism causing the high sensitivity to G.
So after applying this mixed precision fix for the FC2 input, what did the error decomposition look like then? Was activation error still dominant?
Things became much more balanced. With the FC2 input handled at 8 bits, the remaining activation error from other layers and the weight error became much closer in magnitude. The ratio R between them got much nearer to 1.
So neither one is clearly dominating anymore.
Pretty much. And interestingly, at those very high data to parameter ratios, high DN, where we know weight error grows faster with D, the weight error could actually become slightly larger than the remaining activation error after the FC2 fix.
Wow, okay. So that's a really practical insight. If you're doing W4A4 QAT, step 1 is maybe deal with that FC2 input, use 8-bit precision there, or perhaps some other technique specifically targeting outliers at that point.
Seems like a very high leverage intervention, yeah.
And once you've done that, the game changes. Then you need to think about optimizing both weight and activation errors because they're contributing much more equally, especially if you're training on massive data sets.
That seems to be the implication. It's not just about activations anymore once that primary bottleneck is addressed.
And how does this whole approach compare to previous scaling laws for QAT? You mentioned this one is unified.
Right. The key advantage they claim is that this single law captures the impact of N, D, and G together. Previous work might have ignored D or G, or maybe they had different laws or adjustments needed for different granularity settings, different G values. This aims for one consistent framework.
And does it predict better?
They show quantitative results suggesting it does. Compared to prior methods, their proposed law achieves significantly lower relative prediction error for the W4A4 quantization error, including the effect of D, the training data volume, seemed particularly important for boosting accuracy.
Did they connect this to other metrics people use?
Yeah, they briefly showed how you can use their scaling law to predict something called the effective parameter multiplier, or EPM. EPM basically tries to quantify the effective capacity of a quantized model relative to its full precision counterpart.
And why is EPM useful?
It helps you make trade-off decisions, like is moving from W8A 8-bit weights and activations down to W4A4 worth it? Does W4A4 retain enough effective capacity? Their scaling law predicts EPM, and their results suggested the W4A4 EPM is often greater than zero point 0.5, implying it can offer a better compute performance trade-off than just sticking with higher precision in many cases.
Okay, great. Let's try to wrap this up then and summarize the key takeaways for you, the listener.
All right, first big point. We now have a much better unified understanding of how 4-bit QAT scales. It's not just model size N, but critically, also training data volume D and quantization granularity G.
Right. And remember the really interesting kind of counterintuitive finding. Using more training data, D, can actually increase the quantization error gap. Even though the final QAT model might be better overall, the penalty for quantizing gets bigger relative to full precision.
We also learned that activation outliers are a major pain point for W4A4, and they seem particularly concentrated at the input to that second feed-forward layer, the FC2 proj input, likely due to the preceding SWIGIOU function.
But the good news is there's a practical fix. Using mixed precision, specifically targeting that FC2 input with 8-bit quantization while keeping the rest at W4A4, significantly cuts down the error, especially for coarser granularities.
Yeah, highly effective strategy. And looking forward, once you've handled that specific FC2 bottleneck, optimizing W4A4 QAT really becomes about balancing both weight and activation errors because they contribute much more equally then. And weight error becomes increasingly important as data sets get larger.
So hopefully this deep dive gives you some crucial insights if you're involved in making these powerful LLMs more efficient through quantization. Understanding these scaling behaviors and bottlenecks helps you make smarter choices about training and model design.
Absolutely. And building on that last point, considering the paper showed weight quantization error, W4A16, really ramps up with more training data, pushing that DN ratio higher. It leaves us with a provocative thought. What kinds of new algorithms or techniques might we need specifically designed to reduce weight quantization error for 4-bit QAT, especially as we head towards training models on truly massive, maybe trillion token scale datasets in the future?